I am sharing my screen. Okay, today we will talk about sequence processing with deep learning. Okay. Sequence, classically in deep learning, the sequence processing starts with recurrent neural networks. And let's look at what the basic idea of recurrent neural networks are. And it is not actually that difficult. Remember the first example that I gave you at the beginning of the semester? I said that, let's say, we have the temperature, humidity, and pressure values for Gebze. I have taken like day 1, day 2, day 3, and I did this for many days, and as a result, let's say for that day, if it is rainy or not, okay, 1-0, cloudy, sunny, okay, so I have, let's say, 3 outputs. Maybe for day 1, if it is 20 degrees and 30% humidity, 1000 millibars of pressure, and a rainy day, and no clouds and no sun, okay, something like that. We looked at this problem at the beginning of the semester, but we assumed that it was like pressure, humidity, temperature, okay. We have a like this one was connected to everybody, and this one is connected to everybody, right? And this one is connected to everybody. So there's a full connection, and maybe a second layer, and maybe the third layer is our output layer, and in my output layer I have sunny, cloudy, and rainy outputs, 3 outputs. Okay, so this is what we have assumed. Let me in fact do this. Okay, these are the inputs, these are the outputs, and these are again fully connected. I am not going to draw everything, but you get the idea. Okay, and these are connected to the output. Okay, output layer. So we said that I give the pressure, humidity, and temperature, and I get the whether what I think about the weather, sunny, cloudy, or rainy. Some people say that it is very important to what happened. It is very important to know what happened yesterday. Okay, if yesterday's pressure, humidity, and temperature is such and such, then I should make a decision accordingly. Okay, and the previous day, and the other day, and the other day. This one just takes a single day of measurements, and it outputs its estimation. Okay, the better thing would be, let's say, if it is like a box, the better solution would be I would take, let's say this is my box, P1, H1, T1, this is the first day, and then P2, T2, H2, and P3, T3, and H3, and as it goes like that. Okay, so get as many days as possible and output my estimate, sunny, cloudy, rain. That would be better, right? Because I am not trying to make an estimate by looking at the today's result. I am, okay, by today's measurements, I am making an estimate by looking at the today's measurement, yesterday's measurement, the way before estimate, and etc. All of them. So that would be better, but the problem with this one is I don't know how many days I should go back. Okay, if I have 100 days available, that would be better, but if the 100 days is not available, what am I going to do? Am I going to use 90 days, 50 days, 30 days, and etc.? I don't know. So, I mean, using a fixed size input like this is not a very good idea, because I don't know how many days I'm going to go back. The second one is getting the training information for this one is difficult. Why? Because I have only measurements for the 100 days only, right? If I have a network like that, there are many parameters in it, and I have only one chance to optimize this network, and that wouldn't be acceptable for deep learning or any kind of machine learning approach, a general machine learning approach. So I should do something else. That's where this idea of recurrent neural networks come. They say that, okay, you are going to use this architecture here. You are going to use this architecture here. It is exactly the same. You will give me this P0, H0, and T0, the day number 0. I can produce some results here, but when the next day's pressure, humidity, and temperatures come in, okay, I will use exactly the same network architecture, but this time I will do, let's say, this is my internal vector, let's call it this S0. For P0, H0, T0, there is an output also, there is this S0 vector, which is 1, 2, 3, 4, 5 numbers, my internal state. I would keep that one, okay, and I would do this, okay. These are my inputs: pressure, temperature, and humidity for time t. I would input this, and I would multiply with this weight matrix, and this one gives me the state t. And to form the state t, I would get my state from the previous one. If t is 1, this one would be S0, and I would multiply them with another weight set, and I would get my current state by looking at the result of the current input values and the previous state. Now this is my current state, and by multiplying with the output weights, I would produce my outputs, whether it is sunny, cloudy, rainy, windy, snowy, etc. Okay, so that's the idea of recurrent neural networks. You keep your internal state from the previous network run, and you feed this internal state along with the current inputs to update your current state. Okay, so your input is always 3 numbers, and you keep running this over and over and over and over again. Okay, you have a question?
Yes, when we use batches, for all the instance, we use all the ST-1?
Yeah. Yes, it is always ST-1, and this W, U, and V are fixed for this whole network. So it is not like, remember what did I say? I said that if I do that, there would be many more parameters for this network, and I would need only one opportunity to train it. I need to provide all 100 days of input at the same time. I am not doing this anymore. I am saying that, okay, this is my input weight matrix, this is my output weight matrix, and this is my new matrix that deals with the previous state. So I have introduced some more parameters, but that's it. I didn't make my network 100 times as large. I just added these. Okay. So in a way, I am kind of doing this, right? That's where the recurrence comes from. Okay. it repeats itself. Tekrarlıyor kendini. It repeats itself. And that is used. That's used a lot of places. If you have any sequential data, like your measurement of the weather data for the consecutive 100 days, 1000 days, okay, doesn't matter. I can take them all, and it doesn't matter if I have this measurement for 1 day, 2 days, or 3 days, or 100 days. It can fit in here, no problem. And my network doesn't need so many parameters because it doesn't need 100 days of input. These are all nice positive things about the recurrent neural network. Okay, remember what we said. If you have large enough number of nodes in your hidden layer, you can learn anything you want. So why don't we learn data related information? Okay, time related information. This one calculates the time, this one calculates the current measurement stuff, and these would be our outputs. Okay, usually we show it this way. This is kind of another way of showing things. This is my input number 0, input number 1, input number 2, and input number 3, and these are my recurrent state updates from the previous states, and these are my outputs: output 0, output 1, output 2, and output 3. Okay, this is what happens. And again, for input 0, it could be pressure, temperature, humidity for day 0, day 1, day 2, day 3, and it goes that way. And or it could be something else. It could be, for example, words. For example, ben okulu çok severim. Okay, tell me what should be the outputs are. Output 0, output 1. What do you think I should? What kind of output would be good for this kind of a network?
Next word?
What?
Next word maybe.
Next word maybe, yeah, well, maybe. When you say ben okulu could be the next word. After okulu it is çok. After çok it is severim. After severim it is dots. Right? So it knows which word should come next. So it's kind of learning what word should come next. It would be very, very useful. Or I could say ben is pronoun, okulu is the subject of this sentence, çok is an adjective, severim is like a verb. Okay, so I am doing like a part of speech classification for this sentence. I can do that too. Okay, so anything that is time related, sequence related, can be done using the recurrent neural networks. Note that I don't know the number of inputs actually. I mean, I don't know how many sentences I have in my input. Okay, how many words should I have in my sentence, or how many days of measurement should I have, or how many video frames I should have. I don't know. It will all work with any kind of sequential input, one-dimensional sequential input. So if you have a one-dimensional sequential input where the order is important, then think about RNNs, okay, or similar stuff. Okay. So this is the architecture of the simple architecture of the RNN network. As you see, S is updated, my internal state S is updated by multiplying the current input with this matrix. Okay, remember a fully connected layer is actually a layer with a matrix, two-dimensional matrix, and you multiply your input as a vector, okay, with that matrix, and then I multiply my previous internal state with the W matrix, and I put them together and I pass it through this function S, okay, function F, sorry. Function F is like a sigmoid, okay, it is activation function. It could be anything. Okay, so I can do this, and my outputs are it is from G V times ST. Okay, again G is, for example, a softmax function. So nonlinearity comes here. Output you already know. Okay, any questions on this? Any questions from the online audience? Anybody? How many people do I have at the online people? I have 7. Okay.
No,
You have a question on the side? No, he doesn't have a question. Okay. Then yeah.
What's the main advantage of this approach? It is
So, I mean,
accuracy or
It knows the sequence, okay? It knows the sequence, that's one thing. The second thing is that I don't have to know the number of inputs that I should have. 1 day, 2 days, or 3 days, 4 days, 5, it works. The third one is it can relate the closer inputs to each other even more, okay? The far away ones that are more irrelevant to what is happening right now, and I don't have to increase the parameters, network parameters a lot, because all I need is just a matrix for the input, a matrix for the previous state, and a matrix for the output. Okay.
smaller network?
It's a smaller network, and it knows about the sequences. You don't have to fix the number of inputs. You don't have to say this will be the number of inputs. These are some desirable features of the RNNs. Okay. It doesn't work very well with the 2-dimensional data. Okay, it needs a 1-dimensional data, but usually this is what people do. By the way, this shouldn't be, I mean, let me not confuse you. The parameters of this network, W, okay, W, what was others? W, U, and V, okay, W, U, and V, W, U, and V, they are all common, okay, they are all common. So this is not a separate network than this one, okay? They are all the same network. So the number of parameters are very, very small compared to the alternative solutions, okay. So do I miss anything? In theory, yeah. Building models of sequential data is important. Speech recognition, 1-dimensional data. Machine translation from one language to other language, that's another thing. Natural language processing, etc. Recurrent net not used for that kind of a purpose. Here, usually when you say ben okulu çok severim, you don't say I like school very much, because as soon as you see ben, you don't output I, because the word order of Turkish and English are different, right? First you see the whole sentence, then you start producing your output. This one is used for machine translation, but it is not used like I show you. It uses some encoder-decoder structure, and I'm going to show you in a few minutes about that. Okay. Yes.
So I have to use this part in the input layer, or can I use this block in the, for example, hidden layer?
No, this is your whole network.
Only the input layer. So which means
Well, these are your inputs. You multiply your inputs with this matrix, right?
yeah.
So let me show you. Okay. It's
For
like
example,
this.
Can I apply this recurrent
Yeah.
for example, in the hidden layers? For example, from the previous layer, I can pass one of the layer and connect to the other layer.
Well, in this picture, you have only one hidden layer. You don't have more than one hidden layers. Okay, so this is the standard definition. If you like to have more than one layer, yes, you can, and I'm going to show you how to do that. Okay, but for this one, let's say I have 3 inputs. Okay, let's say I have 1, 2, 3, 4, 5 nodes, and I will connect each one to nodes there. Okay, like this, and also I will have 5 nodes here. 1, 2, 3, 4, 5. Why? Because my internal state has 5 nodes, and these 5 nodes are connected to each of them. Okay, maybe you should use a different color. Use a different color. Okay, so all these green ones are from W. Okay, W are green ones, U are the blue ones. So I need that many parameters there. How many parameters do I need for the U? U has
3 times 5.
what?
3 times 5.
3 times 5, 15.
15.
Yeah, yes, exactly. 15 for U, 3 times 5. And how about W?
25.
5 times 5, exactly. 5 times 5, 25 for the W. 3 times 5. So this is a matrix and this is a matrix. Again, for the V, again, if I have this many outputs, 1, 2, 3, again, you know, the 5 times 5, maybe 25 for V. You had a question?
Can I ask a question?
Just a minute, Farshid. There is somebody else asking a question. Yeah.
No, it's okay.
Okay, you go ahead. Go ahead, Farshid.
From what I learned, this network uses at every iteration data from previous step. Am I right?
Yeah, previous step, and then previous step, previous state, but the previous state is formed from the previous state of the previous state, right? So this way, it can get information from the initial input, the input number 0. So
that was I was about to ask. So we should have some initial guess for
yeah,
our data.
yeah. So what should be the S0 then? Because there is no S minus 1, right? What should be the S0? Usually you put zeros in there, or just random numbers, sometimes the average numbers. So there are some solutions, but you should start with some numbers, usually zeros.
And another question, we only use one step the previous. Can we use 3 steps from the previous time?
Well, you could. That would make another type of recurrent neural networks, but that training that kind of a network would be a little bit difficult.
Okay. I'm asking this because this kind of network, I've seen this in fluid finite element or finite volume in CFD. In that area we did such a things. So I wanted to know if it's applicable here or not.
Well, I mean, I'm sure people have tried it. I mean, in deep learning, usually what restricts us is usually the training step. You may design very, very creative, very, very well thought networks. If you cannot train them, they are useless. Okay, your idea might be something good, but back propagation works with the previous state only. Currently, it works best, and that's what we are doing.
Thank you, Hocam.
Okay, good. Any other questions? Okay, let's see the training phase of this one. I mean, training this kind of a network is easy, right? I mean, your outputs are here, inputs are here. Given these inputs, what are my outputs? The difference would be my loss. Try to minimize loss through the back propagation and train it. But this time, okay, my outputs, my inputs, but this one depends on the previous inputs. And to form this one depends on the previous inputs. Because it goes all the way. What am I going to do? The idea is this. Okay. Idea is back propagation through time. If I unroll this network, it is unrolled like this. Okay? This is, let's say, this is S0, this is S0, S1, S2, and S3. Okay? So let's say S0 is all zeros, like I should ask. Okay? This is input number 1, input number 2, and input number 3. Okay? Every time I get this input, I produce the result and I get the state 0, state t minus 1. I get this and I put it in there. So, and these are my final outputs. So I will calculate my loss at this point, and I will back propagate the error like this, and like this in 3 ways. If I continue unrolling my network, this time unrolled it like 2 times. If I unroll it 10 times, 10 times unroll, okay, this will look like a 10-layer network, and I know that I can train 10-layer networks, no problem. If I continue unrolling even more, then I will run into this vanishing gradient problem, because remember vanishing gradient problem? If you take too many derivatives with respect to the others, derivative with respect to this parameter and that parameter and that parameter, your derivatives will get, your gradients will get 0 values all the time. So your back propagation will not work because your parameters are not moving anymore. So I cannot do this unrolling more than 10 times. So I can go at most 10 times back while doing the training. For the runtime, it doesn't matter, because for the runtime, I'll start with the input number 0 and go that way. Okay, so this is called back propagation through time, and recurrent neural networks are trained this way, using back propagation through time.
John, can I ask a question?
Sure.
One thing is confusing me. The number of the hidden layers is here dependent on the number of inputs.
No. Number of hidden layers is 1. Number of hidden layers is 1. Number of nodes in your hidden layer depends on you. Okay? It is your decision.
If we want to have more than one hidden layer, just like normal networks.
Somebody asked this question in a few minutes ago. If you like to have more than one layer, I am going to talk about it in a few minutes. In a few 10 minutes maybe. Okay? Well, I mean, you are free to design your own thing. You can have more than one hidden layer. But the way it works is a little bit different. We'll talk about it. Okay? For some reason, using many hidden layers in recurrent neural network doesn't work. I think we will try at most two or three. Okay, 2 or 3. But remember this, recurrent neural networks are good for one-dimensional data. Okay? So that data is usually time-dependent data, like the sentences, or the speech data, or the natural language data, or the video data. But you might say that, but video is 3-dimensional. I have time dimension and I have 2-dimensional video images. So this is what I do. I get video frame number 1, video frame number 2, 3, 4. These are 4 frames up to frame number 100. So my task is this: get a video of 100 frames and try to classify what the subject of this video is doing. Is he jumping? Is he running? Is he sitting, and etc. So this is called action classification or action recognition classification. Okay, so what am I going to do? This is what I do. Okay, I feed this frame number 1 to a VGG network, but I don't take the classification results out. I take the final 4000 96 dimensional vector, okay? And this vector will be an input to my RNN. And I do the same thing here with the VGG. Again, this vector and this vector would be input my RNN, and do this way and this way and this way, okay? And I take my output from the last element of this RNN. Doesn't matter how many frames I have, 100 frames, 50 frames, 1000 frames. All I care is here my output at the final RNN run, and I would use it as my classification, running, sitting, or jumping. Okay. So again, my data is again one-dimensional, but there are 3 dimensions in it. Most important dimension for me here is the time dimension. For the other 2 dimensions, I am using this VGG network. Okay. So you could do this kind of stuff to get to the time dimension, which is the most important in terms of action classification. Good? Okay, so again, you might say that why don't we have more than 1 layers? You have 18 layers here, like you have 18 layers there. Your hidden layers in your time dimension is very limited, just 1. But total, you have more than 20 layers in this network. Okay, good. So I would, of course, what is my back propagation in this case? My loss is here. I would propagate the loss like this, like that, and like that. But if I go 2 way back, all the way to the F1, so I have to go back through 100 layers. That would make very nasty back propagation problems. That's why I go at most 10 layers or so. Okay, good. So back propagation through time does that. Okay, we train the unfolded RNN using normal back propagation, standard stochastic gradient descent. In practice, we limit the number of unfolding to around 10 steps, and it is computationally more efficient, and we don't run into a vanishing gradient problem in this case. Okay, so vanishing gradient is a big problem. Exploding gradient is another big problem. That's why we cannot go more than 10 steps. Okay, I think I am going to look at this language modeling stuff, natural language modeling stuff, although we will have separate class for this language modeling or the natural language. Let's make a small introduction first, and later we can talk about it. But I think I am going to take some time. Let's give some break, 15 minutes. Okay. Let's continue around 17:05, and let's open some windows to get some fresh air.
Hocam yoklama için buna yazalım mı?
Ha, olur ya, ben onu unutmuşum ya, kusura bakmayın. Başka yere sıkıyor.
Deep learning.
Ya kodu ne kodu?
655.
655. CSE 655. Tarih neydi?
Tarih
23.
11.
Ya.
Yok tamam tamam. Herkes abi. Okay, so let's look at this language modeling. What is language modeling? Language modeling is, of course, it is modern machine learning. It is trying to build a mathematical model or software model or a statistical model for a natural language, so that given a sentence, for example, a statistical modeling, what is the probability of I like computers? Okay, the statistical model will assign a probability between 0 and 1 to this sentence, and I should compare it with I like. Okay, which one is a higher probability? Of course, the first one. Okay, is a higher probability. Is grammatically correct sentence, and it is semantically no problems. It has a meaning. The second one doesn't have a grammatical structure to it. It just says I like. I mean, I expect a noun here, not another verb, right? So, so I would say that the probability of this one is larger than. So it's a probabilistic model, statistical model for this language. Can we have a neural language model? Okay, or NLM. So using a neural network, we will try to assign probabilities to sentences, or we will try to say things like, what would be the word just after this one, or that kind of stuff. That's what we are going to. That's what we are trying to do. Here's an example. For example, if somebody says yesterday it was sunny, so today it must be. Okay, sorry. Yesterday it was Sunday, so today it must be dot. Okay, or space. What should we do? So a model would guess this. I would put all kind of possible words in here, and I measure their probabilities. Whatever the highest probability word, I would put it in its position, and I am using the statistical model of the language. Can we do this using the neural models? Traditionally, starting from 1960s, we use n-grams. N-grams is, for example, good is just one n-gram, one word. But when you say good man, it is a 2-gram. Okay? So how many times do you think good man happened in Wikipedia? Okay? It is kind of easy to maybe measure it. All you say is good man, okay, site wikipedia.org. When I say this, it happened 12,000 times. So this good man bigram happened 12,000 times. How about good, tell me a nonsense word. Good eye. I don't think that it happened. Well, I am good. So I am good, I am gone. So it ignores the comma in here. So do I have good eyes anywhere? So these kind of weird cases, it happens, okay? How about good, another verb maybe?
Good best.
What?
Good best.
Pass?
Best.
Good best? Yeah. Well, it happened. It happened almost 500 times. Where are they? Maybe end of sentence. Yeah, good, best of. Goods best, etc. So as you see, I mean, in statistics, in probability, there is no zero probability. Everything can happen. Okay. So n-grams kind of try to measure it. If you have large corpora, if you have large data set, you can measure the probability of everything. Some of the probabilities will be very, very high. So your language model say that I like this one, okay? Some of the probabilities will be low. You will say, I don't like this one. Let's say you are doing a language translation from English to Turkish, and you have two alternatives. You would choose the one that produces the higher probability, okay, with the n-grams. So why are we talking about the n-grams? Because although n-grams are very, very simple, up until 2010, 2015 maybe, nobody were able to exceed them in terms of performance until they came up with these neural network ideas, RNNs, LSTMs, and transformer networks. Nowadays we are doing better than the n-grams in terms of performance using neural models. Okay, okay, I'm going to skip these. Okay, language modeling with neural networks. To be able to use words as input to our networks, so remember AlexNet? AlexNet. You give a 224 by 224 input image, and it produces one of 1,000 classes, right? So the input is fixed, 224 by 224, okay? That many numbers, 200 by 200, it is 40,000, right? Numbers, more than 40,000 numbers given to AlexNet, and it produces just one of these results, that's it. What am I going to do if I like to give words to these RNNs, okay? Remember, I like to say, I like ice cream. I like to say this, I like ice cream. How am I going to give this I, or like, or ice cream as input to these RNN stuff? So I need to represent I as a vector, like as a vector, ice cream as a vector. So one idea is use one-hot encoding, right? One-hot encoding. And this is what we are going to do now, okay? Let's say in my dictionary I have only 3 words: dog, bites, man. Very, very primitive language, very, very primitive. So I am going to use a 3-dimensional binary vector, one-hot encoding. Dog is 100, bite is 010, and man is 001. One-hot encoding, okay? So if I like to give this sentence, dog bites man, I would give these vectors to T0, T1, and T2. Man bites dog, okay? It's like this one, okay? So that's what I do. So what is this? This is dog bites man, right? And let's say I'm trying to do positive negative classification. Is the dog bites man negative sentence or positive sentence? I guess it's a negative sentence. Okay, so this one should produce a 0, otherwise it should produce 1, and etc. So that would be one case. But what problem do you see with this approach? One-hot encoding for the words. What problem do you see?
It uses too many resources, too many bytes.
Well, let's say in this dictionary I have only 3 words. In Turkish dictionary you have 40,000 words, right? What does that mean? It means that my vectors for each word will be 40,000 dimensional. That is too much binary stuff. Okay. Other than that, you cannot represent a new word that doesn't happen in a dictionary, right? Okay. In Turkish dictionary, I don't think that in Turkish dictionary you have the word for a village that is located in Africa, right? You don't see that word in Turkish dictionary because that's a village name, but it's a name, right? it's a word. So what am I gonna do? This representation is not good. Also, if you like to kind of relate the words to each other, that's going to be a problem. Okay, that's going to be a problem. For example, what is the distance between cat and refrigerator? Okay, let's say this is refrigerator, this is cat. So 1 bit difference here, 1 bit difference is there. If I take the XOR, it's going to be like 2 bits are different. The same thing will be this refrigerator and, for example, a spoon or knife. So these distances between the words doesn't make any sense. I like to have words that are close for these two words. Okay, the distance between cat and cats should be very small, but the distance between cat and refrigerator should be large. So what am I going to do? This is what I am going to do. Okay, in 2013 they came up with this. Well, the idea was there before, but in 2013 they used this with a neural network. Okay, efficient estimation of word representation in vector space. Its name is word2vec. From words to vectors. Okay, that's what it does. Okay, so to assign probabilities or to assign vectors to words, okay, we are going to use this idea. You shall know a word by the company it keeps. Just look at the words around it. Okay, this is what we are going to do. Can I select these? Okay. Okay. I will take a sentence from Turkish Wikipedia, just 5 words. Let's say su buharı tepkimeye hızlı girmez. Okay, so word WT minus 2, word WT minus 1. This is word T plus 1 and T plus 2. Okay, I have a network here. It will take the one-hot encoding of these 4 words as input, and it will try to produce this word in the center. Okay, this is just a simple network, very simple, one hidden layer network. Okay, one hidden layer network. This is called continuous bag of words, and sometimes I just do the opposite. Give the center word tepkimeye and try to estimate these. Okay, so what is so special about this? I can do that. The special thing about this, okay, remember, this is one hot encoding, one hot encoding, one hot encoding, and one hot encoding. Okay, how about this? What am I going to do? I'm going to do this. Okay, I am going to give this, what was the words again? Buhare. Buhare is as an input. Okay, one hot encoding. I will give this, so there will be a matrix here, and there will be another matrix there, and this will produce tepkimeye. Tepkime. Okay, one hot encoding. I am interested in this hidden layer values. Okay, this is 40,000 dimensional, 40K. This is again 40,000 dimensional. This is only 200 dimensional. Okay, this is only for 200 dimensional. So when I give this buharı, okay, buharı is going to be 1 here, rest of them will be 0, right? Because this is just one hot encoding. So that means what? This one will be connected to everybody. So these 200 numbers I kind of represent, okay, these weights, these 200 numbers kind of represent the word buharı, right? And the same thing will be in the other side. One of them will be 1, the rest of them will be 0. This one will represent tepkime. Okay, these 200 numbers will represent tepkime. So in a way that this network assigns vectors to each one hot encoded word. Okay, so instead of using these one hot encoded words, I would use these 200 dimensional representation of the words as input to my networks like that. Okay, my networks like that. Okay, so give the 200 dimensional vector, another 200 dimensional vector, and another 200 dimensional vector. The thing is that the vectors of I and U and V will be very, very close. Okay, will be very, very close, but the vector of I and refrigerator will be far away. Okay, like and want will be very close, like and study will be far away. Okay, ice cream and cake will be close, ice cream and fuel oil will be very, very different. Okay, so that's the nice part of it. So if I am assigning a positive value for this sentence, a positive sentiment, I like ice cream, we like ice cream probably will get positive assignment too, because the vectors are so similar. Okay, the vectors are so similar. That was the nice thing about it. Okay, word to vec, and it got very popular. People use it a lot, and it works amazingly well, and it is fully unsupervised. I didn't mark anything, right? All I did was I took the Turkish Wikipedia, feed it to this network, give it as a one hot encoding, and take it as a one hot encoding, and I saw that this hasta, hastane, hastanesi, hastanın, hastalar, hastacı, etc. Their vectors are very, very, very, very, very close. Okay, and in fact,
can we ask a question?
Sure.
Can you go up to one slide, please, and to the network? Okay. Each word in the dictionary has its own vector. Am I right?
Each word at the beginning has its own one hot encoding, but when I feed all of these data, all of these Wikipedia data, each one will form a different 200 dimensional vector in here, right? So I use that one to represent the word itself. So each word will have a 200 dimensional real valued vector. Okay, it's not a binary vector anymore. It's a real valued vector.
So there are weights on the connection between H nodes and the vector. For example, if xk is 1, we will have weights, and the hidden layer will produce another value if y. You say it is 1. 1 means in another word in the dictionary. So what this network does actually finds close words together, close words, or it does something else. I couldn't understand this part.
Yeah, well, it has to do that, right? I mean, remember what I do. When I say su buharı tepkimeye hızlı girmez, okay, it is very possible to see this sentence in Wikipedia, right? Also, it is very possible to see su buharı reaksiyona hızlı girmez, okay? So I expect that these four inputs should produce both tepkime and reaksiyon. Okay? So tepkime and reaksiyon should have very similar vectors. So because their meanings are similar. Okay? Otherwise my loss values will be very high.
So we give some words to it, some words of a sentence, and the output line will give us all the possible possible inputs for the missing word.
For possible output for the missing word, but it should be logical because remember this is a training step, okay? Whatever it produces, that should be inside the training set. Wikipedia is a very large set. Yeah.
Our training set is the dictionary.
Not dictionary, it is Wikipedia.
Wikipedia.
I open Wikipedia, okay? Let's open Wikipedia, okay? From this one, in computer are two inputs, best words are two inputs, okay? So these are my four inputs, okay? These are my four inputs, and I like to estimate the signs, okay? That's one training. And then computer science and worst end, these are my four inputs. I want to estimate best. And continue this way, okay? Take these two and these two, which performs minimum number are four inputs. I like to estimate the word the. Okay?
So it does this by using that middle 200 most layer.
Yeah, after training like that, each word, since this is a one hot encoding, right? Each word has its own one here and one there, right? So whatever is connected to this one, these 200 numbers are my vector numbers for this word, xk.
Okay, thank you.
Okay? Okay, another questions? So far I didn't say anything about deep learning. This is not about deep learning. These are very shallow network, just one hidden layer, and I'm talking about that. But as I said before, we use these numbers, we use these vectors to represent our words in deep networks. For example, a network like that one, a network like this one. Remember, this could be very, very deep because remember each input is another layer. You may think of it as like that. If your sentence is like 30 words long, then you have a network of 30 layers. Yes.
Do we continuous program first and skip ground approach at the same time? Do we use?
You mean on this one?
No. Other one.
Which one is other one?
Previously,
Which I don't know. I mean, should I go back?
no, forward.
Tell me the sentence. Which one?
And this time.
So I mean, I took these 5 consecutive words. I fed it in here. So I slide my window one by, and I tried those 5 words and slide it one by. So I trained this network. How many times I trained this network? The number of times I trained this network to run the spec propagation is the same as the number of words in Wikipedia. It should be about billions, right? We are talking about billions. So pretty good opportunity to train it. And the nice thing is that it is all free. I don't have to label anything. Okay? Fully unsupervised. And we were looking at some results. Okay? Examples of types of semantic and 9 types of syntactic questions. Semantic syntactic word relationship test. I can get this, okay? The relationship between Athens and Greece, Astana and Kazakhstan, Angola and Kwanzaa, Chicago and Illinois, brother and sister, okay? The relationship between brother and sister is the same as grandson and granddaughter, okay? So it's kind of take the vector difference brother and sister, okay? The vector between brother and sister. If you add that vector if you add that vector to grandson, you get the vector of granddaughter. Really, just know this kind of semantic relationship. Okay? So, semantic relationships, these are the syntactic relationships. Okay? What is the difference? I mean, they take the difference between easy and easiest and add the same difference to lucky, you will get luckiest. It knows about the syntax too. Okay? This was very surprising, but it happened. And it is all learned. It is all learned in an unsupervised way, and it produces very meaningful results. Okay, so I'm going to skip this part. We already talked about it. So advantages are just a neural network, and we don't use word2vec as an application of its own. We use them to produce vectors, and those vectors will be very useful in our applications such as machine translation or sentiment analysis or the text summarization or finding relevant messages from a very large pile of message data and etc. Okay, so that's good. If we go back to this model again, our inputs could be words instead of other stuff. Later they measured the performance of this stuff. Okay, this perplexity is the measurement of how well a probability distribution predicts a sample. So lower the number, better the model, and it looks like this is the one of the best 5-gram language models of English, and recurrent neural language models are doing better than those. And these are from 2015 numbers. Okay. Nowadays there is no comparison. We are doing much better than 5 grams or n grams of before. Okay. Good. Okay, I will skip this part. We know softmax already. Let me get these. Okay. So RNN performs forward neural networks for language modeling. Okay, and we have RNN kind of a feed forward network, but it has this time dimension to it too, sequence dimension it too. So we are better than fixed input forward neural networks and n-grams. Okay, and there is no going back to the other ways of doing stuff. Okay, so I will skip this one. Neural net language models. Let's look at some of the actually neural network models, and this will be more. This will make more sense. Up to now, we kind of used these kind of networks. We give one input, we obtain one output. We gave the image, AlexNet or VGG gave us the classification. Okay, this is one type of network. This is another type of network. We just give one image and we produce many outputs. Obviously, there is an RNN thing going on here, right? So this one takes an input, it produces an output, but the internal state goes there and produces. We don't give more than one input, just one input. This is just one case for the image capturing. You give one image, okay, your RNN produces the caption for the image. Okay, these work very well, and we are going to see. The other one is you give many inputs, okay, like a sentence. It produces just one output. And just give me one example for this kind of a network. What do you think?
Positive, negative language.
Yeah, the sentiment analysis. You say, I like ice cream very much. This is a positive sentence. Okay. I don't like I don't like such and such. This is a negative one, right? This is a negative one. So sentiment analysis is one example. How about this one? This one waits until the input is done, then it produces the outputs. What kind of? Efendim? Alo. I have to take this one, sorry.
Hocam, many to many can be translation.
Yes, machine translation, right? So Turkish in here. Dersteyim acil mi? Tamam oldu. Heh, tamam. Oldu tamam. Okay. Okay, let's take 10 minutes of break. After the break we will continue. Okay, let's be here around 17:46. Bir dakika arkadaşlar ya, belki de dersi iptal etmek olacağım ben yani. Bir dakika.
Hocam,
Enişte anne o hastanede yokmuş. İstanbul'un diğer tarafına gösteriyor. Dikkat gerekirmiş. Arkadaşlar ya, ben dersi bitireceğim ya. Annemi hastanede unutmuşlar, gidip almam lazım. İlk tedavi oluyordu da. Ayarlamıştım. Kusura bakmayın. Guys, I have to cut this class short, sorry. I need to go to the hospital for some non-emergency situation. I guess we will continue next week from this point. Or maybe this. Maybe I will record the rest of this class on video and I will post it. Okay? And you will continue. If you have any questions, you may ask me next time. Sorry for doing this, stopping this early. Thank you.